Okay. So for the bell work, let's go ahead. We'll just go through each of these one at a time. Asked to identify, I said the zeros. I probably should have been, to be a little bit more precise, said the x-intercepts. But what are the x-intercepts that we see for this particular function?
-1, 5.
Fantastic. So we've got 1 at the point -1, 0, 1 at the point 2, 0, and then 1 at the point 5, 0. Now, we spent Friday kind of taking a look at the equations of functions, specifically breaking them down into their factored form, and then using that factored form to make kind of predictions about how the graph would behave, how that function is behaving around certain points, particularly around the zeros. Now we're being asked to kind of reverse engineer that. So rather than being given a function, working our way backwards, kind of trying to figure out what the function would look like here, based on how the graph looks, based on what we see in terms of multiplicities. So for instance, let's start with what's going on at 2. I think that one's a pretty good place to start. As we get really, really, really close to that 0, as we kind of zoom in there, what function does this start to really pretend to be? What kind of function do we start to see? Yes, an even. More specifically than an even, I would say this looks like a quadratic function. This starts to really, really kind of pretend to be quadratic. In other words, around this 0 or for this root, x minus 2, we would expect this to be squared. It's going to be a times some kind of combination of the roots. Around -2, we'd expect this to be squared. What does that tell us about the multiplicity? If this is acting like a quadratic or a second degree polynomial, what is the multiplicity going to look like? Sadie saying it, I saw 2. Absolutely. It's behaving like a quadratic in this case, bouncing off of the x-axis, then we have a multiplicity of 2. Okay. What's going on over here at around 5? What is our function kind of pretending to be? Almost linear in that we're cutting through, but are we cutting through quickly or slowly? So we're cutting through slowly, so I would say that this is looking like it might be cubic. So we might describe the multiplicity as being like 3, or as we would say in our equation, this would be like x minus 5 cubed. And then what's going on around -1? We're cutting through quickly, straight line almost. This is acting very, very linear. That's just going to be to the power of 1. This would have a multiplicity of 1. Now we can be very, very confident in this whole multiplicity of 1 business. It looks like a linear function. Less confident about this multiplicity of 2, multiplicity of 3. We looked at Friday. We said, well, multiplicity of 2 and multiplicity of 4 kind of look very similar to each other. Multiplicity of 3 and multiplicity of 5 and 7 and 9 also look very similar to each other. That's why I asked for the minimum multiplicity that you would expect. So if it's hard to tell apart what's going to be a multiplicity of 2 or a multiplicity of 4 or a multiplicity of 6, they all bounce off just at different kind of speeds almost. Because that's hard to tell, we'll default to assume that it's 2. Right? The minimum value that this multiplicity could be is 2. Likewise, here, the minimum value that multiplicity could be is 5, or 3, certainly could be 5, certainly could be 7, certainly could be 9. We're going to not make any assumptions here. We're just going to say it's at least 3. Okay, and then the reason why I claim that this is kind of poorly phrased, it would be better to say identify the x-intercepts, is because what this doesn't tell us is if there are any complex zeros. So this is a really good way to identify the real zeros, but we still have no idea if there are any other like imaginary numbers that are being kind of, multiplied in. So no idea with regards to that. But should be noted that it is certainly possible, and in fact, we'll look at here in a second why we actually know for a fact that there are a couple of those complex zeros. All right. Couple of other things to talk about for this one. Using the multiplicities here, I make a claim that we can come up with a minimum degree for our polynomial. All right. So the fact that we have these real zeros, the fact that we have these repeating zeros, first of all, what is the degree of our polynomial? When I say the degree, what am I referring to? It's the maximum power that we see when we like multiply everything out and get that really long chain. That's like our a sub n x to the n term. It's that value of n, the largest power that we see. And so if I multiply all of these out, I've got 2x minus 2's, I've got 3x minus 5's, I've got 1x plus 1. If I multiply all of them out, what is my largest power of x going to be? 6. It should be 6. So this is the minimum degree kind of from the multiplicities. Would tell us that that is 6. Where did you get 6 from, Sumera? You have the right idea in that we're going to be combining these powers. We don't combine them with multiplication, though. We combine them with addition. So adding up the multiplicities gives us kind of an estimate for what the degree could be. Right, so in this case, 2 plus 3 plus 1 gives us 6. Again, this is not great because we don't know if there are any kind of imaginary or complex zeros going on. Right? So this gives us an estimate. It's not a great estimate, and so we had another tool to kind of allow us to check this, and that was the tool of turning points. Right? So this zero check is not terrible, but it's not great. We need to check with turning points just to be like extra certain of what's going on. So looking here, where do we have turning points? -3, not at -1, but at -2. Where else? Like 0-ish, maybe like 1/2, whatever that is. Yes, definitely at 4. Good question. Maybe something going on there at 5. Who knows? And then at 2 as well. So ignoring 5 for now, we'll put this in kind of our back pocket and we'll come back to this. I would say, just looking at this, my turning point count would be 5. So number of turning points. I would say a reasonable answer here would be 5. I would certainly, if this were a quiz or test, I would have accepted 5 here. That would be great. And so if we have 5 turning points, what is the kind of number of times that we would expect to cross through the x-axis? How many degrees could we end up with? Other way. Think, for instance, how many turning points do I have for a second degree polynomial? I have 1 turning point for a second degree polynomial, so how many degrees would I expect to have if my polynomial has 5? We'd expect 6. We'd expect the minimum value of the degree, the minimum value of n to be 6. Okay, but it is not 6. In fact, the correct answer here is 8. But again, if you'd said 6, that's great. That looks really good. There's some trickiness going on here, though, that can tell us, and we can use to kind of eliminate down and get to the fact that it's 8. First of all, I want to return to this question mark, which is kind of technically not a turning point. We don't switch directions ever, but like a turning point, we do slow down as we approach that point before picking back up. We just don't switch directions. This actually has a special name. This is not a turning point. This is called a saddle point. And the interesting thing about saddle points is it's like two turning points happening at the same time, right? We are slowing down. We are kind of picking up one turning point. We stop directions, and then we switch back directions immediately. It's effectively two turning points here. And so really when we see the saddle point, we want to increase the count of our turning points by 2. And so rather than having a min degree of 6, we would instead have a min degree of 8. Think, for instance, if we just cut straight through, the number of turning points wouldn't be the same. But when we add zeros there, when we kind of change it to a cube, that's going to change as well. So that's one clue. Again, didn't expect you to know that. We did not talk about saddle points last time. And so 6 would have been a perfectly acceptable answer. The other clue, though, is that our min degree here estimates 6. But we have one turning point with zeros that are not accounted for. Notice that every other turning point is kind of sandwiched between zeros, with the exception of the saddle point. Again, the saddle point is a little bit different, but all of our other turning points are kind of, again, with the exception of this one, kind of trapped, sandwiched between zeros. And so the fact that we have a turning point here that is not sandwiched between zeros, we turn before we hit the x-axis, means that we have complex zeros. All right. That is all coming from this turning point right here that turns before we hit the axis. If the real zeros predicted 6 for our minimum degree, I'll go ahead and tell you that every time we have a situation like this with complex zeros, that's going to add another 2. That's another way that we end up with this kind of min degree of 8 here. We will actually look tomorrow or the day after, probably the day after actually. We're going to look at a theorem called, I think, the complex conjugate theorem that says basically that if you have one complex root, then you have 2, which is how we know that we're adding an additional 2 on account of this turning point that doesn't pick up any zeros. All right, so 6 is a fantastic answer here, but now we know, hey, saddle points add 2 to the number of turning points, and so 8 is a better answer, but again, 6 would have been totally acceptable. All right. Then finally, for C, based on both the degree that we got for B as well as the end behavior, we are trying to figure out what could A sub n x to the n look like. So what's a proper value for A sub n? And then we already kind of established what n could be. So for instance, what did we say our value of n is here? What's n going to look like? X to the x to the what? X to the 8th, at least, looking like x to the 8th. Okay. That's just our conclusion from B. And then what do we notice about the end behavior for this particular polynomial? As x moves to the right, as we move to the right, just in general, as we move to the right, what is our function doing? It's negative, so it's decreasing, which means what has to be true about this A sub n? Also has to be negative. What's a good example of what it could be? Any number that would fit that bill? -1, sure, why not? But that could have been -10, it could have been -100, it could have been -2, -3, whatever. I just said what could be this first term, which is any negative number times x to the power of a. Yeah.
What does the sub n represent in that?
Yeah, so we are going to look at this kind of index a little bit later. It is technically referring to the nth term of a sequence, where the sequence is what you get when you line up all of the coefficients in reverse order. So if our polynomial was, let's say, like had the coefficients, we'll say like 3x squared plus 4x minus 12, then the sequence that we could use, well, it's not even really a sequence. N is just like the a sub n is like the coefficient that matches to the power of n, is maybe a better way to think of it. And we'll see that there is a sequence link later when we do this. But essentially, when the power of x is equal to n, we refer to this term, this a sub n, to tell us what that coefficient is going to be. So for instance, if I wanted to know in a polynomial like this, if I wanted to know what a sub 1 was equal to, I would just say, okay, I'm going to look at where is my x power equal to 1. That tells me that this is going to be 4. It's like just like an indicator to point you in the correct direction. Yeah. So the n doesn't really do anything. It just tells you where to go, basically. And we'll explore that a lot more in depth when we look at sequences, because that has some really cool applications when we do that. All right, good question. Any other questions from the bell work here? Any questions in general from the bell work here? Yeah. It could be negative, anything. The important thing here was to note that because we are falling down to the left and down to, mostly down to the right, but also down to the left, that this value needs to be negative. That was the only thing. The 1 didn't actually matter. It could be -3 or -7 or negative whatever. It just needs to be negative. Other questions? Yeah.
Unit 1 tests. We get those back.
So I don't hand back out the test, but if you would like to go over the results of the test, either office hours would be a good time, or like once we're done with the lesson, if you want to just quickly like take a look at the test with me, then we can do that as well, because we should have a fair chunk of time, so we can definitely do this. Yeah. All right. Let us, yes. Say again. Yeah, you get negative something times x to at least the 8. Technically, could be the 10, could be the 12, whatever. But we know it's at least to the 8. Yeah. All right. Let us then take a look at 2.4 here. The 2.4, at least as far as kind of the ideas or the process, we're going to be taking a trip back to like 4th grade with what we're doing as far as the math is concerned. So that is very exciting. but we'll kind of address here kind of what we're going to run into. What we're going to be covering today is long division. Now, when we are talking about long division, division of polynomials, the other kind of piece that always goes hand in hand with this is synthetic division. I am not going to talk about synthetic division at all. I do not know how to do it. That is information that I very actively have thrown away from my mind. I've had opportunities to kind of relearn it for the sake of teaching it for this class, and I have very aggressively tried not to do that, because why learn a set of steps when you can just understand the fourth grade process of division and apply that exact same logic to polynomials? I think that long division is a lot more intuitive about kind of what you're trying to do, and ultimately is the same thing as synthetic division. Synthetic division just makes it look a little bit different. And so to that end, if you are just the world's biggest synthetic division fan, if like you like sit outside of like protests for long division with like save synthetic division signs, I will not stop you from using synthetic division. That is fine. I will not mention it on the classworks where it says use synthetic division to blah, blah, blah. You can disregard the use synthetic division part. I just want you to do the division. Ultimately, if you get the right answer, then that's fantastic. But also, if you ask me, how do I do this with synthetic division, I'm going to say, just do it with long division. If you would like to ignore me and use synthetic division, that is fine. Just do it correctly. And also, I will not be able to guide you on that synthetic division journey of yours. That will be one that you must undertake yourself. But we will go over long division together, and they're the same thing. So that should be totally fine. Before we talk about long division, though, I want to talk about something that might be a little bit new, and that is the division algorithm. Although, again, we are back in fourth grade math, which means I'm going to make this look like something that we have been doing for years and years and years and years and years. But it's going to start out by looking like something that is not familiar and not very nice. The division algorithm says that we can take any polynomial p of x, we can write it as a product and sum of three other polynomials. So p of x equal to d of x times q of x plus r of x, where d of x is like our dividend, q of x is like our divisor, not like is, and r of x is our remainder. Okay. Looks very foreign. Again, you've been doing this since fourth grade. If I wanted to, for instance, divide 49 by 6. So before we started thinking about like representing these as fractions or as decimals or whatever, and just we're going through the steps of division, how many times does 6 go into 49 evenly? 8. And what is left over? 1. Okay. Another way to represent this fact is to say that 49 is the same as, is equal to 8 times 6. That gets us as close as we can get. But then what do I have to do after I do 8 times 6? What do I have to tack on at the end? I have to add whatever that remainder was. I have to add that one. So exactly like what we were doing in fourth grade, where we can divide a number by some other number. We get as close as we can to actually fitting it in, but then we have to tack on some kind of remainder to kind of adjust for error. Okay. We could do it for any number as well, actually. Technically, just numbers are, in fact, polynomials. They are 0th degree polynomials. We should be able to do this for any number. For instance, we could take 27 divided by 4. How many times does 4 fit into 27? 6, with a remainder of 3. So I could write 27 as 6 times 4 plus 3. Right? And these two are equivalent statements. They're saying the same. Now we pretty quickly stopped doing this whole like remainder of 1, remainder of 3 idea. This is like really nostalgic of thinking about these kind of remainders. What we kind of started defaulting to was if I wanted to take 49 divided by 6, we would really write this as 8 and 1/6. Where what is this 1/6? Well, it's our remainder divided by this thing that we are dividing by. In this case, we might say better yet, this is like 8 plus 1/6, where this is really just our remainder, and this is just our quotient. We'll see that come back up here in a moment, but just to kind of prime with what you have been doing for many years. And the point is that we can do the same thing with any polynomial. And in fact, we will see that we can do the same thing with any polynomial. All right. Now, as far as the division process itself, it really is just division like what we were doing in 4th grade. It's just, we got some variables now at this point. So in this case, we are dividing 3x minus 2 into this polynomial that we are given. So we will write this out as 3x minus 2 dividing into 6x to the third plus 11x squared minus 31x plus 15. Exactly like what we are doing in terms of division. And our goal is super simple. The goal is to find the number that when we multiply by that number, it's going to make our kind of first line of division like cancel. Our goal is to match this 3x with whatever is next. So our first step here is to match 3x to this 6x cubed. Again, this is exactly like what you guys have done for division for years and years and years. If I want to divide 6 into 497, what do? Well, we say, how can I get really, really close to, well, we start with 4. Can't get really close to 4. How do I get really, really close to 49? I multiply by 8. And what do I do with these two numbers? Subtract them. And what happens with the 7? It drops down. Exact same thing. Exact same thing here. How do I get 3x to match to 6x cubed? What do I need to multiply by? So 2 will match the coefficients, but then how do I match the exponents? So I need to multiply by a 2x squared. Okay, so let's do that multiplication. 2x squared times 3x is 6x cubed. These two should always match. We found the number that we wanted to multiply by trying to match them. So they should always match. 2x squared times negative 2. Negative 4x squared. And what am I doing with these two? I am subtracting these two values. All right. 6x cubed minus 6x cubed is 0. That's the point of doing all this, is to make it 0. Okay. 11x squared minus negative 4x squared is not 7, 15x squared. You're always doing subtraction here. And then what do I do with all my leftover bits? They bring them down. We drop them all down. And we repeat this process again. How do I match 3x to 15x squared? What do I need to multiply by? Multiply by a 5x. Okay, that's going to match my first term. 5x times negative 2 is? Negative 10x. And what am I doing with this? Subtracting. 15x squared minus 15x squared. 0 should always be 0, will always be 0. That's the point of doing all this, is making it 0. Negative 31x minus negative 10x. Negative 21x, very good. And dropping down that plus 15. One last one. How do I match 3x to negative 21x?
So,
Positive or negative?
positive.
I want to match it. So I need a negative 7 in order to match. I want it to be the same as this negative 21 so that when I subtract the two, they cancel. So multiplying through, that's negative 21x plus 14. What am I doing with these? Subtracting them. Negative 21x minus negative 21x. 0. 15 minus 14. 1. Can I make 3x look like 1 without dividing out of x? No, we're done. All right. As soon as we can't make the 3x look like a 1 without division, we're finished. All right. So what is that 1? That is our remainder. Okay. Yeah.
Is plus 1.
Yeah, so what ultimately, how are we going to write this in terms of our division algorithm? We can take that initial polynomial, this 6x cubed plus 11x squared minus 31x plus 15, wow, I don't know what that was, plus 15, and say that this is equal to the thing that we got through division. This is 2x squared plus 5, I'm actually going to miss a little bit more room. Equal to 2x squared plus 5x minus 7 times the thing that we divided by. And it almost gets us there, but what do we need? We need to tack on our remainder, plus 1. So that's the division algorithm. The other kind of way that you might be asked to present your answer, Pearson will ask you to do this, is by taking that remainder of 1 and kind of similarly to how we wrote out 8 with a remainder of 1 over here, turn it into this 8 plus the remainder over the thing we divided by, so like the 8 and 1/6. And so you might also see this written as like 2x squared, plus 5x minus 7 plus 1 over 3x minus 2. Where we're just taking the remainder, dividing it by the thing that we divided it by. Exactly the same where this 1/6 came from, right? Remainder divided by the thing that we were dividing by. Questions with our division? Should we take a look at one that's maybe a little bit trickier? Yeah. I'm going to look at 1D here. This is so we're dividing x squared plus 6x plus 5 into x to the 5th plus 16x cubed minus 12x squared plus 20x minus 3. Okay, a couple of things here. One thing that I want to note before we just kind of dive in, what are we missing?
X4.
We're missing an x to the 4th. Okay, that's kind of like missing a place value in our division. Yeah,
So we just do 0x.
yeah, so to make sure that we don't make a mistake, technically it's not like super necessary, but just to make sure that everything lines up really nicely, I would write this out as having there be like a 0x to the 4th. Okay, so I'm gonna have to erase what I did. And we'll write this as there's like this invisible 0x to the 4th here, just to kind of remind us, it's like place values, right? It's just to remind us that that's there, plus 16x cubed, minus 12x squared plus 20x minus 3. Apologies in advance, this one gets a little bit large. But our goal is the exact same. We are always just trying to match x squared with whatever we see kind of sitting out in front. So how do I match x squared with x to the 5th?
X cubed.
We need an x cubed. Very good. All right. X squared times x cubed is x to the 5th. That's good. That's supposed to match. X cubed times 6x is going to be 6x to the 4th. X cubed times 5 is 5x cubed. And what are we doing with this? Subtracting. X to the 5th minus x to the 5th is always going to be 0. 0x to the 4th minus 6x to the 4th is
Negative 6/4.
negative 6x to the 4th. And then 16x cubed minus 5x cubed is 11x cubed. And what do I do with everything else? Bring it all down. Okay. And we repeat. How do I match x squared to a negative 6x to the 4th?
Negative 6x squared.
Negative 6x squared. Okay. Negative 6x squared times 6x is going to give us a negative 36x cubed. And a negative 6x squared times 5 is going to give us a negative 30x squared. And what am I doing with this? Subtracting. Negative 6x to the 4th minus negative 6x to the 4th. 0. 11x cubed minus negative 36x cubed. Minus negative 36 is going to turn into a plus 36. That's going to give me a 47x cubed. And then negative 12x squared minus negative 30x squared. I think you are close. I get positive, I think 18x squared. All right, that's like 30 minus 12. And then dropping everything else down there. This is plus 20x minus 3. Okay, to that point, I kind of want to make this because I think that the logic of like what do I do next is pretty seamless. Like it's the same thing over and over and over and over again. But the same thing that we are doing is distributing a negative over again, right? We are doing this negative distribution probably upwards of like 12 times in this one problem, which is a lot of room for you to mix up a positive and a negative in a way that will concatenate throughout the rest of your problem. So wow, I think that this is kind of one of those ones that conceptually very similar to what we have done since 4th grade. Computationally ends up being a little bit tricky. There's just a lot of moving parts. There's a lot of moving parts, and it's easy to switch a positive and a negative. And you're being asked to distribute a negative over and over and over and over and over again, right? And so this just takes, patience. It takes practice. It takes an extreme level of precision, and it's very unforgiving if you make even a single mistake. Welcome. This is, an interesting one in that, like, there's not a lot of direction to give. It's just you do the same thing over and over and over again, and just try not to mess up. So, which is never great advice to hear. Okay, I'd say we're almost done with this one. We got the two worst ones. How do I match x squared to 47x cubed? With a 47x, awesome. This is why I should test my problems before I write them. All right, so that will give us a 47x cubed. 47x times 6x. 40 times 6, 247 times 6 is 42, so I get 282x squared. And then 47 times 5, that's going to be like 200 plus 35. That's 235x, which we are subtracting. And this would be a good opportunity to use your calculators. I've done this problem a few times today, so I can cheat. This is going to be 0, of course. Negative 264x squared minus 215x minus 3. How do I match x squared to a negative 264?
Negative 264.
This is with a negative 264. First one's nice and easy.
Negative 1584x.
Thank you. That's 1584x. And then the last one,
1320.
1320. So, yeah, numbers got a little bit away from me there. Apologies for that. That is correct. All right, doing out the subtraction, negative this. Negative 264x squared minus negative 264x squared is always going to be 0. Negative 215x minus negative 1584x. That's so close to being a negative 1585, where this would be like 1370. We're one short, so that's going to be 1369x. And then negative 3 minus negative 1320, I get a 1317. And can I match x squared to 1369x? No, so what is this? That is our remainder. Which is a little bit nastier looking, but we have a couple of different ways now that we can write this original formula. For instance, we could write it as with the division algorithm, where this is x cubed minus 6x squared plus 47x minus 264 times x squared plus 6x plus 5, except that kind of is a little bit short. We need to also tack on that r of x. That is one way to write that. And then the other one would be to say, well, the result of this division is x cubed minus 6x squared plus 47x minus 264. And then what are we doing? Well, we are adding the remainder over our thing that we were dividing by. So that would also be a good answer, depending on what they're asking for. So bottom one down here is division algorithm. Top one there is like the actual result of the division. All right. Should really check my problems before I write them. And publish them. This is the moral of the story. Questions here? Hopefully the process makes a ton of sense, even if the getting the correct answer bit is, a little bit frustrating and annoying. Hopefully at the very least we know how to do it, even if, it requires a little bit of practice to do it well. So 2.4, 2.5, that's going to be like the next little bundle of units that we're doing. The classwork for that has been posted to Pearson. 2.4 is kind of split into two parts. There is the part that talks about like the actual division process, and then there's a part that talks about the theorems that we actually care about from the division process. Go figure, what we are using this for, surprise, surprise, is finding zeros. We're going to figure out a way to use this whole division process in order to look for these zeros of polynomials, because that is ultimately the goal of every single thing that we are doing for this entire unit. And so to that end, we are going to look at a whole bunch of the theorems tomorrow. That being said, on the classwork, you will see the remainder theorem and factor theorem talked about in the section that is headed as 2.4, but I'm kind of lumping that in with 2.5. So as far as what needs to be finished by, we'll say tomorrow at the end of class, that would be the first 5 questions from 2.4. So anything talking about the remainder theorem, anything talking about the factor theorem, you don't need to do that. You can if you want to. It's certainly not too bad, and it all comes from the division algorithm. But we are going to cover that tomorrow for that. So for that extra kind of bonus point, first 5 questions on that classwork. What is due tonight? 2.1 through 2.3 due at, it says 1 o'clock. Do note that that is using like East Coast time, so it should close like right at midnight. So making sure that we are kind of finishing that up. And then what do we have tomorrow? Hope it does not come as a huge surprise. 2, 1, 2, 3 quiz. Which for now, at the very least, will continue to be on paper. We'll see if that changes in the next little bit. Don't love Pearson's questions, so maybe not. Yeah. Yeah, for sure. Yeah, we can take a look. Let me